properties of the potential geothermal systems. I also use rock and fluid samples to have porosity and permeability estimations. So to give an overview of the talk before going to the presentation, I'm going to start with an introduction on the geothermal energy. Then I'll talk about Mount Meager Geothermal Complex and why this area was selected for this study. And the rest of the talk, I'll discuss the results and how we can interpret them for geothermal studies in the area. So geothermal energy, as you know, is a renewable source of energy from heat that is produced in the subsurface. A geothermal resource is formed by an economically amount of heat in a derivable depth of the Earth's crust, which is an aquifer with enough permeability and porosity to have long-term production at economical rates. So despite the normal temperature gradients in the Earth, when there is a temperature anomaly exists, different definitions are in the literature for the range of reservoir temperatures, which can be seen in the table as low, moderate, and high enthalpy systems. So 28 countries now produce power with geothermal energy. These charts show the top 10 countries with installed capacity of power generation by the end of 2022. It's the most recent one and is changing each year. We see that large portion of the total belongs to these 10 countries and more than 1/5 of the whole belongs to the US. This plot shows how small the installed geothermal power generation capacity in other countries in the world is, comparing with these top 10 countries. However, there are 18 countries, including Canada, that are now searching or studying for geothermal resources or installing these power generations. So how about in Canada? Geothermal potential in Canada is still under study. As of now, Canada doesn't produce any electricity from geothermal energy, but has a goal to shift from the fossil fuel-based energy to renewable source of energies for the net zero emission by 2050. So this map shows the distribution of geothermal potential in Canada. There's high potential of geothermal resources and energy in British Columbia, Northern Territories, Yukon, Alberta, and Saskatchewan, based on the heat flow modelings. So the study area of this talk is within the Garibaldi Volcanic Belt, which is around the Ring of Fire in southwestern of Canada. As shown in this plot, the Pacific Ring of Fire is on the edge of the Pacific Ocean, where several earthquakes and volcanic eruptions take place in the world. Yeah, so John the Fuca Plate in southwestern of Canada and northwestern of the US is subducting beneath the North American plate, which causes the Cascade volcanic arc. And the northern segment of this arc is the Garibaldi volcanic belt, which represent a chain of young volcanoes in southwestern BC and northwestern of the US. It has several thermal springs and volcanic structures. And the most recent eruption in Garibaldi volcanic belt was in Mount Meager about 2,400 years ago, the area of which I'm going to talk about in the next slides. So Mount Meager is in 150 kilometers north of Vancouver. It is between the Lillooet River in the north of the area and also the Meager Creek. It's studied over decades, and the south part of that, below the Pilo Peak, which has lots of data, is named South Reservoir. There are thermal springs available there, which suggest an active geothermal system. You can see the location of main hot springs, warm springs, and cold springs in the area. And the main structures that control the region are these four faults that are shown in this map. The Carbonate Fault, No Good Fault, Camp Fault, and Meager Creek Fault. So why are we studying this area? Starting from 1970s, Geological Survey of Canada and BC Hydro discovered high enthalpy potential geothermal system in Garibaldi volcanic belt in British Columbia. So since then, over 100 boreholes are drilled in the area as shown in this map, but they stopped the project because of drilling into low permeability zones. So there are available historic data for the Mount Meager, which can be helpful for studying other volcanoes in Garibaldi volcanic belt. There are directional wells and also vertical wells for different research or exploration purposes. Some of the boreholes are deeper than 3 kilometers and they show temperature of 200 degrees Celsius at 1 kilometer below the surface. This is the north-south slice through the map. This map shows the distribution of subsurface temperature in the area, which can be higher than 260 degrees Celsius. And based on these temperature data, studies have been done to see the location of potential geothermal resources in the area. So it can be seen that this area was selected as the potential geothermal area for their drilling purposes, but it's important to note that temperature is not the only important parameter in a geothermal reservoir. Permeability and porosity that allows the fluid to flow is also important for to see the productivity of the resources. So in order to reduce exploitation risks of the geothermal resources and prevent drilling into zones with no permeability, we should also evaluate other parameters of the subsurface. So interests in geothermal energy in Canada has led to a multidisciplinary research project at Mount Meager since 2019. It includes different data sets like magnetotelluric, passive seismic, gravity. And so I'm going to share some of the results on this ongoing project in my PhD with the next slides. So here is a close-up of the study area. The lithology is mainly comprising the volcanic assemblages in the northern parts and also the fractured quartz diorite and granodiorite as the basement rocks shown in different colors here. So the rocks are highly fractured in the area and intersected by these four faults, which can provide pathways for hydrothermal fluid and also the groundwater. So different data sets are used in this project. The first set of data is fluid chemistry data. Several water samples are available from thermal springs and also from some of the boreholes, which are shown, the locations are shown in the map. We mainly used the salinity and electrical resistivity of fluid samples, which were measured in the laboratory. The other data that we're going to use are volcanic and intrusive rock samples that were measured for porosity and permeability in laboratory from the locations that are shown in this map. So in addition to porosity and permeability due to the rock matrix, there's also a fracture porosity and permeability exists in the rocks at Mount Meager. So fracture surveys at Mount Meager measured spacing and also aperture of fractures based on the surface measurements. And also the magnetotelluric data, there are three sets of MT data available for this project at Mount Meager. So magnetotelluric survey conducted in 1982 with 7 stations along the Meager Creek. And the next set of data is from the Frontier Geoscience, which collected 30 magnetotelluric stations in 2001. As shown in the map, they covered the higher elevation areas of the South Reservoir. And the most recent one was in 2019 with 84 AMT soundings were measured to study shallower structures in a denser grid. So now we saw which data we had for this project. We can go through the modeling and see the results. First, I'll talk about the resistivity model, and then I'll use the model as a base to estimate the porosity and permeability. I should also note that it's always helpful to have the conceptual model based on the available modelings and results for the development purpose of the geothermal resources. So I used EMpower for data processing and editing. And for preparing the model files for the inversion, I used either the PyMT code or the GeoTools, depending on the 3D inversion code that I wanted to use. The data that I used for this model that I'm going to show is for the 3D inversion was the impedance tensor of 107 stations. I have run 3D inversions using CGG's RLM3D, and I got models with almost the same structures. We assigned topography in GeoTools with 40-meter layers, and then increasing the thickness of layers by a factor of 1.12, and a horizontal mesh size of 75 meters. And starting from 300 ohm-meter half space, the total final RMS misfit was 1.3. So now I'm going to show you different elements of the model and their location and extensions in horizontal plan view, and how they can be related to no good fault shown in this map. And this is also the location of stations and the elevation of the area. So it shows that the key conductor structures are showing here at the elevation of 500 meters above the sea level. We can see C1 extend east-west beneath the Meager Creek, and also conductor C2 extends northward and bounded by no good fault here. If we step down in the model to 250 meters above the sea level, we can see again the conductor C1 exists beneath the Meager Creek, and also we can see C2 along the no good fault. And we have also the R1 and R2 resistor features, which I showed here, which will be talk about it in few next slides. So the C2 anomaly still exists. And as we go deeper, we can see that is going to the northern part of the no good fault. But C1 disappears at this elevation of the zero of the sea level. And in 500 meters below the sea level, we have none of those conductors. So C1 and C2, based on the geological logs that were studied in the area, can be considered as potential hydrothermally altered rocks, which the geological logs show a lot of clay minerals there. They can be helpful for concentrating the flow into particular areas and can act as a potential cap rock of the reservoir. So in these plan views, we saw that how no-good fault control the conductor C2 in the area, which so could possibly provide a pathway for circulating hydrothermal fluid. Now I'm going to show you these elements on the north-south slices to see how Meager Creek fault can affect these results. So in the north-south slices, we can see the spatial relationship of conductors here by looking from the west to the east of the model. So you can see that C2 which was in the south part of the pylon peak and in the northern parts of these sections appeared here. Below the Meager Creek, we have the C1 conductor in the south of sections. So most of the structures in profile 2 and 3 are the same, which makes sense because of the dense profiles that are showing here. So we also see the Meager Creek fault here and the relationship of that with the distribution of C1. And we go further to the next slices. And so we have seen how these two dominant conductors in the area is controlled by local faults, both the no-good fault and here the Meager Creek fault. C1 and C2 are highlighted areas, and they can be, as I mentioned, the possible cap rocks. I should also mention that there is a relatively resistive zone with the resistivity of around 200 ohm meter exactly beneath the surface. So above these conductors, we have that resistive layer with 200 ohm meter resistivity. This shallow resistor is a region where the hot geothermal fluid doesn't alter the rocks. It's near the surface, and the temperature is almost less than about 70 degrees Celsius. So in these slices, I show again in east-west sections from south of the map to the north of the map. Again, we see the C1 conductor, which was along the Meager Creek. And again, we see the relatively resistive area in the exactly beneath the surface above this conductor. It has different thicknesses through the model between less than 100 ohm meter to almost 500 ohm meter at some areas. So, and moving to the north, we see that we don't have the C1 conductor, and the C2 conductor appears, for example, in this slice to the north. So we saw the extension and location and different features of the resistivity model. So if we get back to the outline, we are now going to use different data sets and this resistivity model that I showed to define the conceptual model and also petrophysical properties of Mount Meager. So to build the conceptual model, we need to study the available information about both the geology and also temperature data, which are available through the boreholes that we had in the area. So electrical resistivity, as we know, is sensitive to temperature, clay minerals, and presence of liquid. So the geology interpretation and also comparing that with a resistivity model would be so helpful to have the conceptual model. So we selected one of the profiles in the model that intersected by two boreholes. These wells show two zones with different alteration minerals based on the reports and interpretations, and also the reports that are available in Geoscience BC webpage. So there is an smectite illite alteration zone in the top and a chloride epidote zone below that in most of the boreholes. So in the literature, the resistivity increases from smectite illite to epidote zones, depending on the amount of clay and alteration minerals that are available. We see this increase in the resistivity in our resistivity model as well. So again, here it shows the more resistive layer in the parts near the surface, which shows less alteration minerals because of lower temperature in this zone. So again, we have R1 and R2 resistive features that can be seen here. They can be act as the basement rock, which we showed here. Yeah. So here I'm going to build a model starting by the structures from the AMT model and interpreted by the geological well logs. So I have added those two layers that I mentioned, one layer with higher resistivity that I mentioned, unaltered zone here, and also the second layer as illite smectite clay cap. This should be the C1 in the models that we saw, and this is the C2. So in those two wells, I have added the temperature logs from boreholes, which is also showing an increase in temperature in the chloride epidote zone. Therefore, we evaluated the temperature logs available in the survey area to see how temperature changes regarding the resistivity. So we added these contours maps to build this part of the conceptual model. These are the temperature data showing how temperature changes from 50 to 200 degrees Celsius in this slice of the model. So the dashed contours shown here means that we didn't have the temperature data in these areas and just it was based on the interpolation, but these the solid lines were from the temperature log. So this plot shows the model structures. This is another plot of another section of the model. It's along the Meager Creek, its southwest northeast profile, which has some of the major hot springs in the area, the Meager Creek hot spring and the Placid hot spring shown here. Again, in these maps, warmer colors are conductive features and cooler ones are resistive. We see the relatively conductive pathway through the model. So we came to this slice to see if there can be connected to the location of hot springs. So if you see these relatively yellow parts going to the hot springs in the area, these zone were through the whole model. It has the resistivity of 40 to 300 ohm meter. This can have higher porosity, and so if we have some estimations based on this electrical resistivity of these zones, we can get to a porosity for the potential reservoir zone. So as we know, the porosity is calculated to see how much the fluid fraction is. And there are, in the literature, there are different parameters that affect porosity in the models. So we should consider the effective parameters that relates electrical resistivity to rock properties. The first parameter is fluid resistivity. So fluid that fills pore space can affect the resistivity by its phase and also its temperature, salinity, and the amount that it is in the pore space. So fluid resistivity depends on the salinity, both the salinity and the temperature. This is one of the equations that exist that relates the resistivity to salinity. There are also some charts that can be used to estimate the electrical resistivity of fluids. For example, this one shows the relationship of the salinity to temperature, with solid lines that shows the variation of electrical resistivity in the plot. So these salinities are from some well-known geothermal fields and shown for the reference. And the salinity and temperature, if we have them, we can use such charts to define the electrical resistivity of a fluid in the area, our area of study. But since we had fluid samples from locations I showed in the few first slides, we had samples with electrical resistivity and salinity. So we modified the equation that I showed in previous slide for Mount Meager, rather than just using the equation based on other surveys. So this equation shows the relationship of resistivity and salinity. So since we have salinity for a few boreholes, we can have estimation of fluid resistivity for fluids in the boreholes. And also it's we said that the electrical resistivity is related to temperature. So based on the temperature logs in the survey area, we can consider the corrections of electrical resistivity that we can calculate from this equation for the temperatures that we have based on the borehole logs. So using the temperature data and the salinity data, the fluid resistivity of the fluids in the Mount Meager area can be between 0.15 to 0.8 ohm meter. So now we want to define the expected amount of fluid within the Mount Meager rocks. We calculated a porosity based on the modified Archie's law and the Hutchins-Strickman upper bounds for the potential fluid pathways, which had the electrical resistivity between 40 and 300 ohm meter in the AMT model. So this part is the bulk resistivity based on the AMT model, and this is the porosity that can be estimated. And these solid lines show different fluid resistivities, and that the values are annotating the lines. So as we saw in previous slides, fluid resistivity calculation for the area showed a range of 0.15 to 0.8 ohm meter for borehole samples at the reservoir temperature. So if we consider that zone of higher porosity in the AMT model and consider these range of electrical resistivity for fluid samples, and we can see that based on the cementation factor of 1.6, it can be it can go to the porosity of 0.1 to 8.5%. So this value for the cementation factor I had just one borehole with porosity neutron-like porosity. So we have calculated porosity based on that one available well log and had this estimation for a cementation factor. However, after that, we had some sensitivity tests on how this cementation factor can make change in the porosity. So rather than just having a range of porosity like what I shown, since we had the bulk resistivity from the AMT model through the survey area, we can estimate the porosity by just propagating the fluid resistivity and also the temperature logs based on the boreholes that we had in the survey, and also the Archie's law. So C1 and C2 were the potential caproics that I showed in the AMT models. So we shouldn't consider high porosity in these two zones, since they are not they are related to clay minerals. So as we see the values showing very low porosity in the area, now we have estimated the porosity, but we should evaluate other parameters that can affect it. So here we see the lab measurements. As I mentioned, there are some lab measurements with porosity and permeability values. There are two main categories, if I want to say, the volcanic samples and the basement samples. The volcanic samples showed higher porosity and permeability. We can use the lab result to correlate the porosity and permeability, porosity from the model to permeability. So based on the lab data for the basement and volcanic samples, we had defined the relationships between the porosity and permeability, and we use these equations to just convert the porosity from the Hashine-Strickman model and the modified Archie's law range of porosity that we had to permeability. So we see that the permeability is so low, it's up to 0.25 millidarcies. And to have a productive reservoir, we should at least have permeability higher than 0.1 millidarcy based on the literature. So this is not too high permeability. So as I mentioned, there's a porosity and permeability related to the rock matrix. And also another porosity we have is related to fractures. So we already know that we have a highly fractured basement rock. So it shows the importance of studying fractures in the Meager area. These data were just the surface fracture studies. It's not based on the borehole core data. So using these sets of fractures and also model them, we can have the fracture porosity and permeability. So if we have these fracture sets subsurface, we can have the porosity up to 40% and the permeability up to 666 millidarcy. And they are related to northwest southeast fractures, which are parallel to the regional stress direction in the area, study area. So if we get back to the conceptual model that we were making, and if we follow the pattern of bulk resistivity range of 40 to 300 ohm meter that I mentioned in the whole model, we can also follow the patterns that can be used as the upflow of fluid in our conceptual model. So we can also consider the direction of fractures that were can be productive in the area. So this model is just a conceptual model for the study area, shows a schematic model for the Mount Meager Volcanic Complex based on just geological logs, and also our AMT model and the temperature data. So as a combining of laboratory and laboratory samples, fluid chemistry data, fracture data, AMT modeling, we can conclude that the AMT model showed conductive features as the cap rock, which were mainly bounded by two main local faults, and these conductors down deep along the No Good Fault and above the Meager Creek Fault. We have also defined the components of Archie's law for our study area instead of just using the constant values in the literature. So we estimated the reservoir was related to the electrical resistivity of 40 to 300 ohm meter of electrical resistivity. This zone can be related to the fluid content of up to 8.5% and permeability of up to 0.25 millidarcies. And the volcanic rocks showed higher permeability in measurements than the fractured basement rocks. And considering the pattern of fracture sets for drilling purposes is so important because it can increase the permeability up to 666 millidarcies. So I would like to acknowledge my advisors, Jim Craven and Dariush Motazedian, and I would also like to thank Dr. Steve Grasby for supervising this multidisciplinary project. And thanks to all people that helped in this project. Here is some of the references. And thank you. I'm here for any questions.
Well, thank you very much, Fateme. That was absolutely wonderful. I really like when MT people take their models beyond conductivity, and the petrophysical approach here is absolutely fabulous. You've done a wonderful work. So I'd like to invite questions. Please send them in the Q&A. I'll read out the questions so it gets in the recording, and I'll then ask Fateme to address it. If any of you want to speak, and we encourage dialogue, please just raise your hand and I'll make it available for you to speak. So the first question is from Weijin Zhao. How many faults was inferred from the 3D resistivity model? And are there faults those were not interpreted compared with previously known faults before the 3D AMT inversion? So question generally about faults, how many faults you found in the 3D model?
Yeah, so as I showed in the slides, let me go. So in these slides, I showed that based on the model, we could see the relationship of the structures to the No Good Fault and also to the Meager Creek Fault. So these two main faults show a relationship with the resistivity model. We have also tested so many inversions with using faults as tier surfaces to the model using RLM 3D. So those models actually confirmed the results that we got from the unconstrained inversion that I showed in this presentation. So the No Good Fault and Meager Creek Fault were confirmed to be relative to the conductive features from the AMT modeling. But the other two faults didn't show a relationship to the conductive features.
Mm-hmm. Yeah, and Weijin Zhao has a second question that I think you answered anyway. What's the 3D inversion software used? And you did answer that. It was the CGG software. Okay, on to a question by Assam Aboud. You have many MTs, but you did not use them with your new AMTs. I guess merging both AMT plus MT gives a clear picture about the subsurface.
Yeah, I used the MT stations in the model as well, because 84 of the stations were the AMT sites, and the rest of that I used the MT stations in the model, where, for example, in this area that I didn't have any AMT data, I used the AMT data that were available in the model.
Okay, and Abbas Fanze has got a question, a general question. It's the same one I was going to ask. Thank you very much for your informative talk. Please explain more about the applied result of your work, about the geothermal well you proposed finally in the area. And that's something, a general question is, what are the implications for geothermal energy based on your results?
Just based on my results, so we could just propose the locations, the potential locations for the possible cap rock and the potential reservoir zone. But in real and practical terms, so companies, they will evaluate the fractures, because they have drilled so many boreholes, but they couldn't find any reliable permeable zones to use for electricity or other purpose of the renewable energy productions. So for this one, again, in this is a part of a multidisciplinary project. There is passive seismic, there is gravity, bedrock mapping, and other parts in the project, which at the end, they have to be combined to see what the conclusion will be. But from our point of view, we just propose the potential zones based on our modeling.
Yeah, excellent. So any more questions from the audience? There's a comment in the chat from Bertold Kriegshauser. Very nice presentation. However, there were no MT, AMT, nor log data shown. I guess what we did see was your final RMS. So we know the model fits the data, but generally it would be good to see representative data fits and model misfits. So we know. Yeah,
I just considered the model to reduce the time of the presentation.
Right.
But they can send an email and we can have discussion if they have any question.
So Jerry Roth, who is one of the people involved in the KEGS Foundation, welcome, Jerry. He writes, is Meager Mountain Complex a candidate for stimulation as a hot dry rock geothermal system?
I think it can be considered as the hydrothermal geothermal systems, because we can have the EGS systems or the hydrothermal, because the hot fluid and hot rock exist in the area. So first, I think they're trying to use without using any hydraulic fracturing and these things to have the production, but it depends on the situation.
Yeah, clearly, yeah. So another question from Adas Fanze. Thanks again. Do you have any study in the Sabalan area with very similar EM models? I'm not, sorry, I don't know where the Sabalan area is.
Yeah, it's in Iran. It's in
okay.
north of Iran. No, I haven't studied, in the area, in that area.
Okay. One more question popped in from Buchi Babu Bongo. Basement rocks generally should have less fractured rocks than top layers, but in your case, the basement rock is more fractured. Is it not contradicting the layered theory?
Actually, it's because of it's a volcanic zone with lots of eruptions, and it has also another recent eruption. So these fracturings, most of them based on the literature and geology papers that I read for the study area, is related to those explosive eruptions in the area. But rather than that, they are also have recent bedrock mapping studies, which can be helpful to follow in a Geoscience BC webpage. I think they will share that.
All right, that's, I think you've answered everyone's questions. Absolutely wonderful work.
Thank you.
The recording will be available in a few hours. And Fateme, if you could send me your presentation as a PDF, I'll put that up on the website.
Sure.
So I'll say thank you once again. It was a wonderful, wonderful presentation.
Thank you so much.
Yeah, thank you. And we'll see everybody this time next week. Have a wonderful week, and see you in a week's time. Bye, everybody.